Welcome to the first of 3 lectures that will finish up big idea number 6, which is dealing with equilibrium. I like to refer to this part of equilibrium as ice problems. Part 3 will be continuing to use a lot of what we've been using in the previous 2 chapters. We will be working with acids and bases. We will be working with an ice chart, small k problems, and calculating pHs. What we're really going to look at is how can we apply that information we have already learned to some new situations. And the first thing I'd like to talk about today is what's known as the common ion. And this is going to impact our ice chart with the initial concentrations just a little bit. The common ion is produced by both the weak acid and its salts while in solution. And if you remember, we have talked about salts a little bit before. A salt is just another name for an ionic compound. It's just another name for an ionic compound. So what we'll see is we'll have our weak acid, we'll have the ionic compound or the salt, and they're going to have 2 parts that are the same. So there's going to be a part in our acid that matches a part in our salt, and that is the common ion. Now, the effects of the common ion can be predicted by Le Chatelier's principle. Is it going to shift to the left or is it going to shift to the right based on where it appears in the equilibrium expression? Because it disrupts the equilibrium, that also means it's going to have an impact on our pH as well. And so what we'll be able to do is we will be able to look at some examples where we have just the acid by itself, for example, acetic acid. And then what happens when we add in the common ion? What happens when we add sodium acetate in? How does that change the pH of our solution? Polyprotic acids, and remember that word polyprotic means we have more than one hydrogen ion. They also experience a common ion effect. And if you think about the 3 dissociations or 2 dissociations that a polyprotic would go through, you'll notice that hydrogen becomes their common ion. In each dissociation, they all have that hydrogen ion present. We will continue to work these problems with ice, but what's going to happen is the initial concentration of the A minus. And when I say the A minus here, this A minus, we're referring to that as the conjugate base of our weak acid. All of our other ice problems, that conjugate base started out as 0. But it's not going to be 0 this time because we're going to see that that conjugate base, that A minus that we're going to refer to it as, it's in both the weak acid and it's also going to be in our salt, our ionic compound. And so that's our common ion will be present. So we're going to change that first step, just the I part of ice. From there on, everything is exactly the same as what we've done before. Here's an example. We have a solution of hydrofluoric acid, and there our HF. I'm going to refer to this as our HA. That's just the generic formula for a weak acid. And we have sodium fluoride. Notice our A here is fluoride, and guess what we have over here? We have fluoride as well. There is our A minus. The fluoride is our common ion. And so what we want to do is, how does this common ion impact the equilibrium? How does it compare to a pH of a solution if we only had the hydrofluoric acid present? And so you'll see you have some information on your PowerPoint, but I want to kind of set up an ice chart here a little bit differently and show you what happens. So HA, our weak acid, is what we're going to work with. And so we have our weak acid, arrow goes both ways, and it dissociates into hydrogen and fluoride. And now if this was just the weak acid only in our ice, we'd have some concentration. Let's just make it 1 molar for the sake of argument. And then these would both be 0, nothing there. This is automatically normal problem. So this is just if we have weak acid only. But what happens if we now add in that salt? We add in sodium fluoride and we add in that common ion. The equation's going to start the same way. It's going to start with a dissociation of the weak acid. But what happens is the ice part changes a little bit. If this is 1 molar, we don't have any of this, but let's say we have 1 molar sodium fluoride. Well, 1 molar sodium fluoride, because there's a 1-to-1 ratio between the sodium and the fluoride, that's also going to give us 1 molar fluoride as well. There's the difference from when you have weak acid only and here where you have the weak acid and the common ion, the salt, along with it. It changes that initial step. Now, what's kind of neat about this is it does the exact same thing every single time there's a common ion. The equilibrium is always going to shift to the left, and that's always going to reduce the pH. The common ion always lowers the pH. So that's in your PowerPoint. I'm not going to put it up right here, but make sure you highlight that. The equilibrium shifts left. That's a common ion always does that. And that ends up making the pH less acidic. And we're going to see a lot of uses of this common ion. The first thing we're going to look at is how does this create a buffered solution. So we're going to create a buffer solution. Okay, it's going to click this. What is a buffered solution? Well, right now in your body you have a buffered solution. Your blood is a buffered solution because it resists a change in pH when either a strong base, because notice we just have the hydroxide there, or hydrogen is added. A strong acid is added. And so your body, your blood, is a buffered solution that for the most part it can resist changes in pH. It stays a slightly basic. And let's see how that happens. All buffered systems work on having a common ion. And you can have 2 different kinds of common ions. Sorry, take that back. You can have 2 different types of buffered solutions. You can have a weak acid and its salt, kind of that example that we were looking at prior on the last slide. Or you can also have a weak base and its salt. Now, the key here is in order to have a buffer, you always have to be able to find your HA and your A minus. So your weak acid and its conjugate base. Well, here on the first one, you can't miss our HA. We have our hydrofluoric acid, and the common part there gives us our A minus. Well, over here as well, even on the weak base and the salt, this time we're starting with our base, and we're always going to refer to the base part as the A minus. Well, in our salt, the conjugate acid of a weak base is just the base plus a hydrogen. Well, right here, we have our HA portion. And so we have our buffered solution as well. So we're going to look at both types of buffers that we can create, either using the weak acid and its salt or using the weak base and its salt. So let's try a problem and see how adding in a common ion changes it up a little bit. A buffered solution contains 0.5 molar acetic acid and 0.5 molar sodium acetate. Calculate the pH of this solution. So first thing I'm going to do is I'm going to look at this a little bit and see if I have a common ion. So I'm going to write the formula for my acetic acid and my formula for my sodium acetate. And you can't really miss the common ion. They both have acetate a part of them. Here, this is our HA, and the acetate over here, that's our A minus. Those are the two things we have to have in order to have a buffered solution. We've got to be able to find the HA, we've got to be able to find the A minus. So acetic acid, weak acid, we know weak means ice and a double-headed arrow. So we'll take our acetic acid and arrow going both directions. That'll produce hydrogen ions and our acetate. Our A minus and our HA are present. We'll go ahead and start our ice portion of this. And this is where things are different. We're going to have 0.50 molar acetic acid. We don't have any hydrogen. Now here's the different part. We are going to have some acetate, and that acetate is coming from that salt that we added in, because we know salts are very soluble. They completely dissociate. So we actually end up with 0.5 molar acetate as a part of this problem. That's it. That's the big change here on the initial part. Then everything is the same as what we've been doing before. We have no hydrogen, so it has to shift towards the hydrogen. Our change is going to be minus X, and plus X. So at equilibrium, we end up with 0.50 minus X, and 0.50 plus X. Well, you're asking yourselves, okay, now I got this minus X and this plus X with 0.5 in two different places. And before, when I had small k's, which the Ka for the acetic acid is small, it's 1.8 times 10 to the negative fifth. But when I had those small k's before, I was able to ignore the change in the reactant. Well, that's still going to work now, but here's the cool thing. It works over here as well. This K is so small that we're saying the equilibrium lies mostly to the left, so we're really never going to add anything much over here to the acetate from the common ion. And it's also hard to add it because it's such a great concentration anyway. It's so large to begin with. So from here, back to normal problem that we're used to doing, we're going to write our equilibrium expression. We have our hydrogen ions, our acetate over our acetic acid, and plug in. Our Ka is 1.8 times 10 to the negative fifth. We don't know hydrogen. That's what we're looking for. That's our X. Now, this is the cool part. We have 0.50 on top, and we have 0.50 on the bottom as well. Well, because of that, the math gets super easy on this problem. What you can do is we're just going to 0.5 divided by 0.5 cancels out, and we actually already have x. There is no math on this problem. 1.8 times 10 to the negative fifth molar equals x. And keep doing what I told you to do before. Every time you find x, make sure you mark down what is x. In this case, x is our hydrogen ions. Make sure you mark that. Well, now all we need to do in order to find the pH is to take the negative log of this. And our pH is 4.74. 4.74. So basically, it's exactly what we were doing before in order to work through and solve for a pH. We are making a small correction at the beginning because we do actually have some of our conjugate base, our A minus. And then instead of just canceling out one X, we get to cancel out two X's down at the bottom. So let's figure out, how does a buffer actually work? How does it prevent that change? So we have a buffered solution of our weak acid, HA, and our conjugate base, A minus, to which we are going to add a strong component to. And I want you to watch for that. You'll notice that we're always going to be adding strong things to our buffers. We're never going to add a weak acid or a weak base to our buffer. So first thing you want to do is kind of figure out, what's the chemistry that's got to happen here? If we add hydroxide, what part of it does it want to react with? Does it want to react with the weak acid, or does it want to react with a weak base? Well, because it's a strong base, it has to react with our weak acid. And so here we have our base. Here we have our weak acid. The base is able to accept a hydrogen ion from our weak acid. That makes some more of our A minus, our weak conjugate base. And then over here we have our water, which is acting as our conjugate acid. Well, notice, in a buffer solution, the hydroxide doesn't have a chance to accumulate. We don't have a chance to make it because the hydroxide, as soon as you put it in, it reacts with the weak acid component. And so instead of getting hydroxides, you get some more of our A minus. That's part of our buffer. That's why we can resist the change. Now you'll see down here at the bottom, the pH is governed by that weak acid conjugate base ratio. And what happens is you really want to have really large concentrations of those weak acids and those weak bases, your HA and the A minus. The larger those concentrations are, the better buffering capacity you have, which means you can take on a lot of hydroxide and the pH won't change very much. So ideally, here on this last part, you want to make sure that your concentrations of your weak acid and its conjugate base, its HA and its A minus, are a lot greater than the hydroxide that's added, because then you'll end up with very little change. So let's look at our next slide and actually try one and see what happens. So what we're going to do is we're going to work with the components from that first example problem that we did with the buffer that had the acetic acid and the sodium acetate in it. And we want to see what happens when we add 0.01 moles of solid sodium hydroxide to 1 liter of that buffered solution. What kind of change in pH will we end up with? And I have 3 basic steps for every problem that we're going to work. And so these are the steps. And you got to do them in this order in order for it to work. The first thing you got to do is you need to think about what is the chemistry that's going to happen here. When I add that strong base, what part is it going to react with from my buffer solution? Is it going to react with my weak acid, or is it going to react with my conjugate base? Well, it doesn't make any sense for a base to react with a base. That's never going to happen. So it is going to be absorbed by the weak acid. So let's look at that chemistry step first. And so I'll number it number 1 so you know exactly what we're working on. From the sodium hydroxide, it's only the hydroxide that we're worried about. That's the part of sodium hydroxide that's going to react with our weak acid from our last problem. So this is our base. That's our acid. And let's see what's going to make here. Now I'm doing a one-way arrow here, and I'll tell you why it's a one-way arrow in just a minute. The base will accept a hydrogen ion to make our water. And that will also leave us with our conjugate base, our acetate. So here, we got our HA, that's important. And over here, we've got our A minus. Those are the 2 components that we have to have in order to create a buffered solution. Now, the second step that we need to do is we need to consider the stoichiometry. All of these problems end up being a limiting reactant stoichiometry problem. There's some part that we're going to run out of. And we create a chart to do our stoichiometry, and we refer to it as the BCA. And the way that I remember this is base combines with acid. Anytime you're working a problem and you've got a base and it's going to combine with an acid, or you have an acid and it's going to combine with a base, this stoichiometry part has to happen every single time. Now, something else about this with the stoichiometry, it also always has to occur in moles. Has to be in moles. We got to do stoichiometry in moles. Well, if you notice in this particular problem, everything is 1 liter. Well, the great thing about when everything is 1 liter, molarity will be mole. So we don't have to do any extra math or anything like that. So they told us how much hydroxide we're going to add in, and we have 0.010 moles. From our previous problem, it was 0.50 molar. Well, that's going to be 0.50 moles because it's 1 liter of it. Remember, just like in our last chapter, we don't care about water, so we can just put a line straight through that. And then remember, now we're adding this to a buffer, so we've got that common ion. So from the sodium acetate from the previous problem, we've got some acetate in here. It was also 0.50 molar, so we'll make this 0.50 moles. Now, what are we going to do on the change part? A BCA chart is different than an ICE chart because in BCA it doesn't change by X, but it always changes by the same thing. It always changes by the smallest number of moles. Changes by smallest number of moles. So when we look up here, we've got 0.01 moles of hydroxide, or 0.5 moles of our acetic acid. 0.01 is smaller, so we're going to do minus 0.01 minus 0.01. We're going to lose on the reactant side, and just like before, we're going to add on our product side. So when we come to at the end of the stoichiometry, what are we left with? We don't have any moles of our hydroxide. We've absorbed all of it. We have 0.49 moles of our acetic acid, and we have 0.51 moles of our acetate. Now, the good thing about here at the end of this problem is that we're still in 1 liter. So, just like before where our molarities became our moles because we were in 1 liter, here our moles automatically become our molarities because we're in 1 liter as well. So that's first step, figure out the chemistry. What's combining with what? What's reacting with what? And it's always going to be an acid-base reaction. Second step, work through the BCA of what's going on. Work through the stoichiometry. Do your limiting reactant problem and figure out what you have left. Now the third step, I'm going to put it on a new slide for us. Our third step is actually what we've been doing before. We're back to our ice. So from that previous problem, and you can actually work it either way, we have our weak acid present and we also have our conjugate base present. We're going to do our third step. Which is our ice. So let's work with our weak acid that we had left over from our last step. Our weak acid dissociates into our hydrogen ions and our acetate. Work our ice. We have 0.49 molar of our acid left, no hydrogen yet, and we had 0.51 molar of our conjugate base, our A minus. Same as before, minus X plus X plus X, 0.49 minus X, X, 0.51 plus X. Same small k as before, that 1.8 times 10 to the negative fifth. Because it's a small k, we're going to be able to get rid of both the minus x and the plus x. Now it's just what you're used to doing. Ka is our hydrogen times our A minus all over our weak acid. And plug in 1.8 times 10 to the negative fifth equals x. Now our A minus is our 0.51 and our HA, our weak acid, is 0.49. Now notice they're not the same this time. So you are going to have to multiply by the 0.49 and then divide by the 0.51. And x equals 1.7 times 10 to the negative fifth molar. And remember, we always mark what is our x. And our x is our hydrogen. Because that's our hydrogen, we can take the negative log of that, and the pH is 4.77. That's a pretty good buffer because if you remember when we did the previous problem and we came up with the pH of just the buffer solution before we made any additions to it, it had a pH of 4.74. So adding this concentrated, or so not concentrated, but adding the strong base to this buffer produced very little change. To give you a point of reference, if we added this same amount of strong base to just pure water, if we added it to pure water's pH would go from 7 up to, with the base added in, it would become a 12. Water doesn't have any buffering capacity to it, so it will not resist the change. We got to have that buffer solution to be really good at that. As well, this was our how does a weak acid in its salt prevent the accumulation of hydroxide and resist that change in pH. So let's look at, well, what if it is a buffered solution of our weak acid and our A-, and this time we're adding hydrogen ions to it. First thing we have to ask ourselves, hydrogen ions, what are they going to react with? What's the chemistry that's going on here? Hydrogen's not going to want to react with another acid. That's never going to happen. Hydrogen is the acid component. It's going to want to react with our A-. So our A- reacts with our hydrogen ions and it makes our HA. Notice here we've got both of our buffer components present. We've got our A- present. We've got our HA present. The hydrogens can't accumulate. Instead of accumulating these hydrogen ions, we accumulate the weak acid as the component instead. Same thing as we happen with our OH. You want to keep those buffer components, the weak acid and the weak base, a lot larger concentrations than the strong acid or the strong base that you're adding. As long as you do that, you get very little change in the ratio of your buffer components and you get very little change in the pH. So this brings me to my favorite equation. This is the Henderson-Hasselbalch equation. I will not write Henderson-Hasselbalch out over and over. So it looks like I'm writing a hydrogen molecule, but we'll also refer to it, we'll call it the HH equation. This is the shortcut to getting to pH. Using Henderson-Hasselbalch makes ice irrelevant. You don't have to use it anymore. You can if you want to. I like this because it's a shortcut method. It's a little bit faster. You have to have the A- and the HA. As I like to refer to it, you have to have the AHA, A- and HA. The formula for this, and the one I like to use and remember, is this first one. The pH equals the pKa, and now notice we got the P in front of that. Remember, that just means take the negative log of the Ka plus the log of AHA. That's how you remember the order. You don't say ha, you say AHA. And that's how you remember the order, that it's the A- over the HA. We are going to assume that the A- and the HA are the initial concentrations, which is okay, because remember in the ice chart, when we were doing those previous problems, we crossed out the change. And so our initial concentration did become our equilibrium concentration. So it is perfectly acceptable to do that. So let's work a problem. Let me just show you the first one problem, just showing you how do you use Henderson-Hasselbalch. And it says calculate the pH of a solution containing 0.75 molar lactic acid and 0.25 molar sodium lactate. And you're asking yourself, well, I don't know the formula for lactic acid. Mrs. Gill doesn't know the formula for lactic acid off the top of her head. So I'm going to use, instead of trying to find that formula, I'm going to use this as my HA. And I can tell here, if this is lactic acid, it came from ic, goes back to 8. It came from lactate. That's my A minus. So I have both parts here. Now, one of the things I want you to be careful of, I only have HA and A minus. HA and A minus equal, I'm looking at a buffer. And so this is a more simplified problem. We're just going to go straight we can do a little ice chart, and then we're going to do the Henderson-Hasselbalch equation. We don't have to do BCA. And the reason, there's no strong, so that equals no BCA. BCA only becomes a factor when we start adding in a strong component to it. So we have our weak acid, and it dissociates into these two components, our HA and our A minus. And we do our ice, 0.75, 0, and 0.25. This will change by minus x, plus x, and plus x. 0.75 minus x, x, 0.25 plus x. Ka value is up there in the problem. It's small, so that means we're going to get rid of that. Now, I misspoke earlier when I said we got rid of ice. We don't get rid of ice. What we get rid of is writing the equilibrium expression and then doing a small k problem with the Henderson-Hasselbalch. And the reason that I can do the Henderson-Hasselbalch is because I have both parts. I have concentration of my A minus and the concentration of my HA. So the formula is pH equals, let me switch back to the red, the pKa plus the log of Now, what I'm going to do for my pKa is I'm going to write in negative log of 1.4 times 10 to the negative 4th plus, and then I'm going to put in my concentrations. My A minus is 0.25 and my HA is 0.75. Now, some of you will like to skip steps. I'm thinking Shafi's going to skip a step here. Rob will probably try and skip some steps here. Don't do that. Go ahead, find the negative log, because we're going to do some problems later that you're going to have to repeat this process over and over. And if you go ahead and have the negative log of your Ka written down, it'll save you time on future problems. That is 3.85 plus, now what I'm going to do is take 0.25, divide it by 0.75 first, and then I'm going to take the log of that answer, and that comes up negative 0.48. So the pH of this buffer is 3.37. 3.37. So this problem was just to show you that here's a quicker, easier way to get to a pH. If you wanted to, you could do the equilibrium expression, and then you could do a small k, and then you could solve for the pH. Instead of doing 3 problems, we get it all done in 1 problem. So it does make it a lot faster. And you can actually Use Henderson-Hasselbalch in conjunction with the BCA as well. Let me show you now how Henderson-Hasselbalch works with a base. So you can see that this is always going to work. I'm going to teach you one little extra thing, though, in order to make it work. But trust me, it's easy. So this time we're working with a buffered solution. So I even told you it's a buffer, so you don't even have to guess. That contains 0.25 molar ammonia with a Kb. Now this is a dead giveaway. That's a Kb, so that thing over there has got to be a base. And 0.40 molar ammonium chloride. Calculate the pH of this solution. So let's mark a couple things that are happening here. This we said is our A-, that's our base. Our base plus a hydrogen over here gives us our HA. So we have both parts of a buffer, our A- and our HA. We're going to work this as a base problem this time. And remember to start this off. When we have a base, bases always get reacted with water. That's how we prove that they make hydroxide. So we'll react that. Oh, there's our ammonia. There's our HA component. And there we have our hydroxide. From here, it's just like the other problems that we were working. We'll start with our ice. We have 0.25 molar. Don't care about that. 0.40 molar, that comes from our salt, and 0 of that. Same shift as always, minus x, plus x, and plus x. 0.25 minus x, x, and whoops, I made a mistake. I got in that habit of doing the x's. 0.40 plus x and x. Just like with our weak acid problems, we're going to get rid of the x. Now, we have we have our we have our ha. So we can do the Henderson-Hasselbalch. But where you have to be careful is the Henderson-Hasselbalch doesn't use Kb. The Henderson-Hasselbalch uses Ka. This is a super easy problem to fix. Little equation that we have to remember. Ka times Kb equals Kw. That's all it takes. And you know Kw. It's the Kw we use all the time, the 1 times 10 to the negative 14th. So if we wanted to solve for the Ka, we would take our Kw that we have and our Kb that we have and just divide them, and we'll end up with our Ka. So 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th gives us a Ka of 5.6 times 10 to the negative 10th. That is one of the things you have to be careful of with Henderson-Hasselbalch, is it has to be the pKa in there. So using our Henderson-Hasselbalch equation, pKa, the log of we'll take the negative log of 5.6 times 10 to the negative 10th plus the log of our A minus, and our A minus was 0.25, and our HA was 0.40. The negative log of that is 9.25 Divide first and then take the log plus negative 0.20. This buffer has a pH of 9.05. 9.05. So Ka is working with either the weak acid buffer or the weak base buffer, pretty much the same process. If you wanted to on this one, if you didn't want to use Henderson-Hasselbalch, you could write your equilibrium expression, you could do your small k problem, you could solve for your POH, and then solve for your pH. So it actually takes 4 more problems to get through this one instead of just the 2 that we did here. So let's combine everything we've learned so far. Let's take a buffer and let's disturb the buffer with something. So we want to calculate the pH of the solution that results when 0.1 moles of gaseous hydrochloric acid is added to a 1 liter of the buffered solution from the previous example. So we're going to work with that buffer that we just worked with, the ammonia buffer. So let me write that up there so we know we're working with, whoops. We're working with this buffer system from before. And so remember the steps. Chemistry, BCA, because we got a strong. And then you really can go 2 different ways here. Ice, or you can go Henderson-Hasselbalch. Okay, chemistry first. What's going to react with what? So we are adding acid in. Acid reacts with base, so we have to go with our A minus, our ammonia. So NH3, our A minus, plus our strong acid. One-way arrow, because this is stoichiometry, not equilibrium. Gives us our ammonia. We're going to do our BCA because we are taking an acid and we're reacting it with our base. We have our strong component. We have whoops, sorry, I'm going to get ready to put that wrong. So let's look at our hydrogen in here. We have 0.1 mole of hydrogen. We are using the molarities from our last problem, but notice once again they gave us 1 liter. So the molarities from our last problem are automatically our moles for this problem. So we have 0.25 moles of ammonia, and we have 0.40 moles of ammonium. Now, remember with the change part, for the change, it's always the smallest number of moles. That's what you're always going to be changing by. So in this case, it's our 0.1, so we're minus 0.1, minus 0.1, plus 0.1. This gives us 0.15 moles, 0, and 0.50 moles of our final component. These are in 1 liter, so our moles automatically become our molarity. And the next thing that I look at when I see this, I go, oh, I'm here to, after the reaction is complete, and I have ha. So that means I can go straight to my Henderson-Hasselbalch equation. I don't have to do my ice chart or the rest, or the small k problem. And the reason I'm going to go straight to, I'm not even going to do my ice chart on this particular problem, is because remember back in the beginning when we were subtracting out our x's and adding our x's in our ice chart, we ignored those. We canceled them out. So we don't even need that ice chart. We know that the concentration of A minus and the concentration of HA aren't going to change. So I'm going to go straight to pH equals pKa plus the log of AHA. And because I write down all of my work and I have my previous example, I know that I already have the pKa from the last problem. I wrote it down and it was 9.25, so I'm just going to plug that in. I'm going to take a shortcut. I am going to write my stuff in here. My A minus is 0.15 and my HA is 0.5. 9.25 plus, we're going to divide that and then take the log, and that is negative 0.53. And so our pH is 8.72. So that was kind of a bit of a change there, because the pH of that buffer originally was 9.05. We added a good bit of hydrogen in there, so it's creating some change, although not as much change if you added this straight into water. It'd be much more dramatic, like we talked about adding sodium hydroxide right into water. It changed the pH by 5 points. So still better than just adding something into straight water. So I have a few last things that we're going to go through, and then a couple more problems that I want to work for you. So kind of my last little buffer items before we work two final problems. For a particular buffering system. So a system where you have your HA and your A minus, or your AHA, however you want to remember it. If they have the same ratio of AHA, then they'll have the same pH. And also, we always have to have that AHA. So we always have to have a buffered solution must always have a weak acid and a weak base present. Now, a little bit more about this, the same ratio part. Let me give you an example of that. If we had 5 molar acetic acid and 5 molar sodium acetate, this would have the same pH, because this is a 5 to 5, 1 to 1 ratio. Well, if we had 0.5 molar acetic acid and 0.5 molar sodium acetate, the ratio is still the same. Both of these have a 1 to 1 ratio. If their ratios are the same, they'll have the same pH. So if you were working a problem and you calculated the pH of this first solution, and then the B problem, the ratio was still the same, you wouldn't have to do any more work. You can just state same ratio as the first problem, so it has the same pH. So that's kind of a little quick trick you can use to get through some problems. Now here, I did mention a little bit about buffering capacity earlier. Buffer capacity, this represents how much hydrogen or hydroxide the buffer can absorb without creating a significant change in the pH. And to get a good buffer, to have a large capacity, so to have a large capacity, you want to have a large concentration of the buffering components. You want HA and A minus to be greater molarities than whatever you're adding in to it. And I have an example of a problem that we'll do, and I'll show you the difference in the buffering capacities. Now, we talk about having the best buffering capacity. So who can large buffering capacity, who can absorb the most hydroxide or hydrogen. We also talk about something that's known as optimal buffering. Who is the most resistant to the addition of the hydrogen or hydroxide? And the best buffering occurs when you have a 1-to-1 ratio between your AHA, your A minus, and your HA. When you have that 1-to-1 ratio, you end up with your pKa being equal to your desired pH. So you can have a optimal buffer or you can have best buffering capacity. You can have both, but they're two different things. A good buffering capacity, large concentrations of A minus and HA, so you can absorb a lot of hydrogen and hydroxide, whereas our optimal buffering occurs when we have a 1-to-1 ratio between our two components, our A minus and our HA. So there's two ways to look at buffers and quantify them. Okay, so we are down to our last two problems, so hang in there just a little bit more. Calculate the change in pH that occurs when 0.010 moles of gaseous hydrochloride is added to 1 liter of each of the following solutions. We have solution A, which is 5 molar of the weak acid and 5 molar of the sodium acetate, and solution B, which is 0.05 molar acetic acid and 0.05 molar sodium acetate. Now, when I first look at this, which one of these solutions is going to have the better capacity for buffering? And the one that has the better buffering capacity is the one that is the larger concentration. So solution A is going to be able to absorb a lot of hydrogen and a lot of hydroxide with very little change. Now, both of these solutions are optimal buffers, because if you look at the ratio of their components, they are both 1-to-1. So ideally, we should have very little change. Our pH should equal our pKa, but we have to factor in the buffering capacity as well. So what I'm going to do for you is I'm going to help you with the chemistry part, and I'm going to give you the answers, but I want you to work through and see if you can get to the answer. Do your steps. So first off, chemistry. We are adding hydrogen ions. We are adding our strong acid. So our acid is going to react with our base. So here, in each one, this is our HA. And our acid molecule minus our hydrogen is right here. There's our conjugate base. Sodium, just along for the ride. So our chemistry that's happening is our acetate, our A minus, is absorbing our hydrogen ions, and it's making our HA. So we've got our chemistry. Now what I want you to do is work through the BCA and work with Henderson-Hasselbalch. And for the first solution, which is the 5 to 5, the pH is 4.74. And so if you notice on that one, didn't change much from our original buffer, didn't change at all from our original buffer pH. It's got a large capacity to absorb. Now if we look at our 0.05 compared to our 0.05, the pH is 4.56. Didn't change a lot, but it doesn't have it doesn't have near the capacity of our other one. So yeah, we're going to see some change occur. So you work through that and show me in class that you came up with those answers. So the last type of problem I want to show you how to do is it a buffer? Because this is a common problem that you'll see, and it's a common mistake you guys make with this is you just look at it and say, oh, I see HA, I see A minus, it's a buffer. Well, you got to consider the chemistry. If you notice on this problem, each one of these has a strong base. Strong bases can't ever be a part of the buffer. So actually what we want to see is at the end of this problem, after we consider the chemistry, so we're going to consider the chemistry first, then we're going to consider the stoichiometry. What we want to do is figure out, is there buffering components left? So I have two steps here for you. The first thing we're going to do is the chemistry. What's going to react with what? And then we're going to do our BCA because we've got A strong. And lastly is AHA left. Do we have any AHA components left? If we have AHA left, then it's a buffer. No AHA, not a buffer. So let's look at letter A. And we have hydroxide. That's what's important. And hydroxide is not going to react with chloride. That's never going to happen. It's going to react with this methyl amine, which is our HA. This is our weak acid component. And when this reacts, our hydroxide is going to pick up a hydrogen from our methylamine and make water. And that's going to leave us with our weak acid minus a hydrogen, which is our A minus. What we want to figure out is at the end of this problem, do we have AHA left? So to do that, we go BCA. Everything's always in 1 liter, so we'll use 0.1, 0.1. Don't have any of this, and don't have any of that yet. But oh, let's not put a line in there. Let's put a 0. We don't have any of that. We're going to make some of it. The change is always by the smallest, so minus 0.1, minus 0.1, plus 0.1, 0, 0, and 0.1. What we want to ask ourselves is, do we have AHA? Well, I have Ah, but I don't have any Ha. So that automatically means this is not a buffer. Not a buffer, because we have no HA left after the chemistry and the stoichiometry occurs. Now, sometimes you can just look at it. Now, we know that this is our base, but from our last problem, what did we learn about CH3 and NH2? That's our A minus. Do two bases ever react? Hopefully you're shaking your head no. Two bases, not a buffer. After there's no chemistry, this one is taken out by step number 1. There's no chemistry there, so can't even look any further. So let's look at letter C, and I'm going to add in a slide here. Letter C, we still were working with the original equation that we had before. We have our OH. We're going to add it to our HA. Get our water and our conjugate base. This is a reaction because we have an acid and a base present. We're going to start off with 0.2 moles of our base, 0.1 of our acid, don't care about water, and 0 of our base. Always change by the smallest, so minus 0.1, minus 0.1, and plus 0.1. This gives us 0.1, 0, and 0.1. Back to our third question. Is there AHA left? Oh, let's go ahead and mark this. I forgot to mark this up here. That's our AH. We have our AH. There's no HA. So this is not a buffer because there's no HA. There's no HA. And we're also left with two buffers. Two bases are left. And every buffer has to have the weak acid and the weak base. So hopefully D is going to work out for us. Working off that same equation again. Here's our HA. There's our A minus. Adding a strong component, so it has to be BCA. This time we're starting with 0.1 of our strong base, 0.2 of our weak acid, and don't care about it, and none of our conjugate base. Our change is always by the smallest, minus 0.1, minus 0.1, and plus 0.1. We are out of strong base, 0.1 of our weak acid and 0.1 of our weak base. Last thing we check, do we have AHA? There's our AH. There's our HA. This is a buffer. Buffer, we have AHA. And that concludes our lecture on buffers. Online lecture number 2 will be up shortly, and that's all about titrations, which is basically just reinforcing everything we've learned about buffers. We're taking buffer information, going to apply it to a new situation.